All right, hello everyone. Welcome back. Welcome back to a new and exciting episode of, what can Eric screw up today? All right. So technically, this is 341. And we're going to talk about linked lists. Let's write the word linked lists better. So, cool. So before we get into live coding and the moral of today's lesson, which is never live code in front of a class, let's talk about everything. So I guess the first question is, if anyone, I guess some announcements. So if you're not on the GL servers, if you're like a transfer student and you don't know much about the GL server, you should send me an email. And I'll work with you to get you on the GL server. So I guess that's one of the first announcements. And then the next announcement is, I don't know. Do I have anything else that's really important? Welcome back. Okay. I see that the number of people's going up a little bit, so hopefully we'll, I'm just kind of padding out a minute or two until we really start. Has Project Zero been released yet? Okay. Does anyone have a link to it that they want to post in the what you call it? We can look through Project Zero for a few minutes if someone shows me a link to it. I bet it's in the 341 Discord. I'm gonna guess that. Let's see if I'm right. You sent a link. You sent a link. I don't know. I don't know anything. Announcements. Nah. FAQ. Maybe? Oh, Project Zero is out. Here it is. Alright, let's see what it is. Okay, so what are we doing here, man? Like, what is this? Okay. The implementation will be done entirely in Q.H. There is no Q.cpp file. Okay. So you're supposed to complete the Q class, so let's look at the Q class. Let's see what's going on here. Yeah, so if you need the project, it is posted in the 341 discussion. I hope that you all can see links that I post because I am the, YouTube. Whoops, did not mean to drag that. I meant to drag YouTube. I mean, Discord. I mean, Facebook. I mean, Silicon Valley. Okay. Okay, so yeah, I might send out a Blackboard announcement with it just so that everybody has it. So let's look at this thing now. Why not? Okay. We're including IOStream and exception. Oh God. So using range error, so that's an exception. Okay. So now we are generating 3 template classes. We're doing a node class, a queue class, and this is just a horrible thing. Does it not work for people? So, okay, let's see what's implemented. Okay, so don't touch anything here. Oh my. Okay, so here's a question. Did you guys actually get the Discord link? Because I'm a little bit confused. Some of you seem to have gotten it, and some of you didn't. And as it turns out, I am not the Discord master for 341. So here's the thing. We need to find out all the people who didn't get it, and I need to make sure that you get it. Yeah, because, well, anyway, it's not technically my job, but I definitely want you in there. I haven't really set up a whole thing like Ben did for his class yet. I don't know if you guys want to all go on teams like he had. We can do something like that if you want, but I'll think about it. Okay, we'll talk about it more. Okay, so yeah, I mean, so don't just leave it in the Facebook thing. I know that I think one of you, and I'm not going to name you because I think you already said it, has sent me an email about it. So basically, I know I might get swarmed with emails, but just send me an email if you haven't got the Discord link invite. Or I have a better idea. Maybe I'll just, I don't know what. I mean, all I'm going to say is that I don't think I could bring myself to naming teams after, like, Pokemon. I don't think I could do it. I'm just not quite that. I'm not quite that way. Okay. Oh, we have to implement a copy constructor, an assignment operator, a destructor, and nothing else. Okay, cool. Okay, cool. So, yeah, I mean, I personally, I don't know. There's, Team Spaghetti. Okay. So actually, I'm not going to talk about Project Zero yet, because I think that this is what you have to do for Project Zero, and as it turns out, if you haven't noticed, we're about to talk about linked lists, and this queue right here is implemented as a linked list. And so if you know how to implement, say, the copy constructor, the assignment operator, and the destructor for a, I don't know what, maybe a linked list, then as it turns out, this is going to be almost identical. So, so we're not going to talk about the I will normally talk about the projects. I'll normally give you some hints, anything that I think. Like, normally what I do is I usually implement the projects myself, and then if there's anything that causes me even like 10 or 20 minutes of problem, or an hour of difficulty, anything that causes me any difficulty, I will be like, aha, and I'll tell you about it. I'll be like, I won't give you all the answers, but I'll tell you a little hint. Like, when I did this thing, I had to be careful of this other thing. I'll say that kind of stuff. And so, but here I don't want to say anything yet because there's no point. Okay, so Project Zero has been released. You have to finish a queue class, but the queue is implemented as a linked list. So, really, what we want to do in life, right, we want, now, like, there's nothing left to do and everybody's here. Well, most of us are here. So now let's get to the point, right? Let's get to it. So what is a linked list? Well, basically, a linked list is, you usually draw it like something like this. This is like the pictorial description of a linked list. And of course you can be like, well, there's a doubly linked list, there's all kinds of things. So each linked list node, so each thing here is called a node, 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 and I don't know, node. And then over here is null. Technically you could use null pointer, or null, or whatever. So in each one of these nodes is contained two things. One is a value, and I'm going to leave it untyped right now. I think in the project it's templated, and we can go over a little bit how to deal with templates. But also, then there's a pointer, which points to the next node. And it doesn't just point to the value, it doesn't just point to the next pointer. I'm just kind of drawing it like the pointer will point towards the whole next node. Like this. So you have another value, another value, another value, another value, and pointer, 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 and pointer. Now, you might ask, like, what's the point of a linked list? Like, why do we do this? Let me actually get rid of this arrow because this arrow doesn't really exist right now. So what's the point? Of this thing? Basically, the answer is it's a more efficient way to store certain types of structures. So if you're just storing an array, right, this is like the worst way to do it, because if you have to access the... Yeah, so as I say, it's the pointer is neither pointing towards the value or the next pointer. It's pointing towards the next... It's really pointing to the next node, right? Like, the next node has its own memory location. So and so basically, I think the primary use of these things are usually in like stacks, queues, things called decks. And sometimes you'll use them to kind of make arrays a little bit less, what should I say about it? A little bit less susceptible to resizing issues, right? Because if you have like a vector in C++ and you add something onto it and it has more space, so if this is your vector and you add one more element, so if you have a whole bunch of elements here and you add another element, that's okay, you can do that here. But if you have a vector like this in C++ and the whole thing is filled up, then when you add a new element, this is actually a really inefficient operation, because what it has to do, or at least what it does in C++, is it actually creates an array of double the size, and then it has to rewrite everything from here into the first half of the doubled array. So all of your data goes into here, and then this is empty space, waiting for stuff to fill it up. And so it's when you hit this one point here, this operation is really costly. Now, of course, you can average it out, and we'll talk about amortized analysis in later classes, but really, this operation, when you hit this operation, basically because it has to allocate double the space and it has to rewrite the entire array into the new array, it does get very costly. So there's actually some tricks that some other libraries use, that instead of reallocating a new array, what you do is you actually just link together a bunch of arrays in a linked list structure. And that way, you sacrifice a little bit of performance when you access further on elements, which can also be fixed by other types of things, but you can also, but basically, like here, if you have an array of fixed size, here's another array of fixed size, here's another array of fixed size. When you get to the end of the array, you don't actually just have to reallocate the entire vector. You can just block on another node which will contain an array. And for so basically the value in that case would be an entire array. So that's kind of the idea, is that most of the uses are for these things, and then the other use is generally in kind of, if you have gigantic arrays for which it would be really, 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 really costly and just like prohibitive to do this kind of vector operation, you can kind of do this operation. But then you also have to kind of fix the inefficiency of, say, having to get to an element over here where you have to be like, okay, I'm gonna keep hopping and keep hopping and keep hopping through the linked list. Okay, so let's talk about operations on linked lists. So basically there's I mean, really, there's like, I mean, I guess you could call it creation. So some people use the term CRUD, where it's like creation, removal, or I forget. All right. Creation read, because D stands for delete. Read, update, and delete. And so we're going to talk about all these operations in terms of linked list. So the first thing that you might have to ask is, how do you create a linked list? And the answer to that is that in a linked list class, you generally at least have to have one thing. And that thing is a pointer that I'm generally going to call phead. And the reason why I'm going to call it phead is because it is some kind of node pointer that is going to point to the first element of the list. So initially, when you create the linked list, it's going to be set to null pointer, which is just also known as 0. And so the idea here is that when you create your linked list, this is what you have to do. And this is really all you have to do. You just set a fixed head pointer to nothing. And so that head pointer is always going to point to the first. So phead is always going to point to the first node in your linked list. Like this. So that's how you can know where to start, because if you just had all these pointers, this pointer pointing to this thing, this pointer pointing to this thing, the question would be, like, which pointer do you have stored actually as a variable in, say, your linked list class? And the answer is this one, right? You have to store the head pointer at all times. So sometimes you'll store a tail pointer, sometimes you'll do some other things, but generally you have to store the head pointer. So this is like the one thing you have to do. Sometimes this is the only private element inside of a linked list class. I mean, it could theoretically be the only private element, is just a node pointer to the head, right? So this node is the head. Okay, so how do you read? Well, so there's two options. That's why I think CRUD is a little bit vague here. There's two ways to read. You can either read by position, or you can read by checking is X in the linked list, right? And read doesn't actually say which one it is, and so really you can implement either one. And so that's anyway, we'll get to that. Update is the same thing. So update, you can either update by position, or you can update by is the thing in the linked list. Like if you can find a 3 in the linked list, change it to a 4, right? So update is something that you can do on linked lists. But generally, update is a combination of like finding something by a position and then removing it and then inserting. So I don't think update is going to be its own function. It'll probably be a combination of like insert and maybe overwrite or delete or something like that, or like get node, something like that. So we'll see what we do with update. And then delete, you can remove nodes. So here's the thing, and deletion also has the same issue. You can either delete by position or delete by value, and just the word CRUD or the acronym CRUD doesn't tell you that. So you have to make some decisions when you implement your linked list. You have to decide what you're going to do actually. So let's show you, let's say that we've created the linked list. So here's our phead, right? What do we do when so phead is currently pointing to null, or null pointer, or whatever you like. So when we insert an element, when we insert the first element, what do we have to do, right? So what we have to do is basically we have to set p head to be the first node. So basically the first element is going to be given a value of, say, v. And so what I'm going to do here is I'm going to say p head is equal to new node, right? And if it's templated, we might have to put in the type, but we'll get to that. For now, I'm just going to leave that off. And hopefully node has a value constructor, so I'm just going to say v. And that's it, right? Because what's going to happen, so what happens when you create the linked list, or when you insert, I really should say insert here, insert. You're going to have p head pointing to the new node. So it's now going to point to this new node here with a value of v. And its pointer here is going to be equal to 0, right? It's going to point to null again. And so that's how the first insertion works. So, okay. So now the question is, how do we insert a new element? Let's say that we want to insert a new element here. So we want to insert something at the head. So actually what we want to do, so now we're going to insert, instead of v, we're going to insert w, right? So now we're going to insert. So what we want to do is we want to set p head to a new node with a value of w, right? But if we did that, then what would end up happening is that p head, well, oh good, actually that's the right position. So p head would point to a node with a value of w, but then how does it know, right? If we do this, and here's the other node with a value of v that's pointing to null. So how do we know how to connect them, right? And so the thing is, you can't create this first when you do the insertion. What you have to do is you have to remember the previous head. So you have to say, like, previous is equal to p head, right? So you have to remember where the head was, and then what you can do is relink the linked list. And you relink the linked list by saying that you're going to say p head next is going to have to be assigned to be the previous node, right? So that's the way to say that and I guess really this is the previous head, right? It's not previous in the linked list, it's a previous head. So but anyway, yeah, so the new head, this is the new head, gets assigned to have its next pointer point to this node here, and that will relink your list, right? So that's how you kind of think about relinking in this case. Okay. So now, how do you insert? Let's say that you have a linked list. Oops. And you want to insert a node here, right? So here's a new node that you've created. You want to insert it right here. So how do you do this, right? So what you have to do is, basically, this is your end goal, right? That's your end goal. So how do you get there, right? So let's imagine that this node is called previous, and this node is called next, right? So how do we link these up? And I don't know, this one can be called current. I'll just call it cur. So what we're going to do is, if we have pointers to all three of these nodes, then we know that what we can do is we can say, we know that previous arrow next, arrow next is going to be equal to current, right? Current arrow next is going to be equal to this next, which I guess I should maybe... And finally, what? Well, so next can also have a next pointer, but the point is that that never gets messed with. So basically the previous .next is equal to the current, and the current .next is equal to this next node. So that's how you generally link up a linked list. Okay, so are there any questions at this point about how this stuff is going to work? And of course, I guess I should say that if there's no next node, right, if next is just null, this is actually okay, because what will end up happening is if next is null, then current.next is just going to be set to null, which is fine, right? All we're doing here is instead of we're getting rid of this connection just pointed to nothing. So then this connection will point to something now, and then it's the current connection will point to nothing. So it's okay if this next node is null. For this insertion operator, it's not okay if previous is null. If previous is null and you try to access its next pointer, then you're going to explode, right? That's no good. No good. So this has to be not empty. Okay? So next can be null, but previous can't be. Also, current can't be, but hopefully current isn't, because it's the node you're actually inserting, right? It's a node with a value in it that you're trying to stick into this linked list. Okay. So now let's talk about removal. So removal works kind of the same way, right? So let's say that we're in the middle of a linked list, and it's coming out of nowhere, right? The head is 100 nodes behind, and for all we know, it goes on for another 100,000 nodes. Who knows? All I know is that I want to remove this one, right? I want to get rid of this guy. So how am I going to do that? Well, basically what I'm thinking of doing here is I just have to think about how I'm going to relink everything. So what I mean by that is that I need to link this guy up to here, and then I need to delete this guy, right? So somehow I have to do those two operations, and that's really it, right? So I mean, and I'll talk about doubly linked lists in just a second, but that's kind of it for removal. So the only other exception is if you're removing the head, right? So if this is the first node, and here's p head, and I'm telling you, you have to get rid of this one. You can't just delete this one first, right? What you have to do is you have to assign the p head pointer here, and then you can delete. So that's the only thing you have to remember. So this is like an edge case. So usually the head is always an edge case because the head is the one node that has a special pointer in a linked list that always looks at it. And so if you're ever messing with the head pointer, or if you're ever messing with the head node, I should say, then generally you have to adjust the head pointer, right? Okay. And so, all right. Cool. Who wants to write a linked list? All right. So, is everyone more or less okay with what I've said so far? Is everyone good with kind of, I mean, this is like theory, but honestly, I think it's a lot of block diagrams, right? So I think I will just write a linked list. So I wrote one last night, but I'm going to literally start a new one. We are going to start a new class. Let me drag down my Visual Studio so you see that I'm not lying. We are going to start add class. We'll call it LL for well, we'll call it what's a good name for a linked list? Linky. Okay. So, what kind of things does Linky need, right? What does Linky need? Well, it probably needs a constructor. Cool. Let's make a copy constructor. So when you're making a copy constructor, you have to do const Linky ampersand, right? Ampersand means what? And then let's have an insert at head. Let's make a really simple one. Insert at head only. So we'll call this method insert at head. And I'm just going to make this int value. So don't worry about, and we'll have a boolean if it was inserted or not. Maybe. We could just make it a void for now. So, and then let's have a remove at position. Well, yeah, let's say I have insert at position, and then we'll have int position. And then we'll have void, well, we'll have bool remove at position. The boolean is just to test if it happened or not. Oh no, we don't need a value, we'll just do int position. And what else do we need? I guess what we need is, let's do an assignment operator. And then we'll need a destructor. Okay, and so for a destructor, it'll be Linky. And then, so all of this needs to be public, right? And then for the private thing, oh no, wait, this is the assignment operator. So the assignment operator is going to return a Linky reference operator equals, and then const Linky reference other Linky. Okay, cool. Now, and then the one private thing is going to be a node pointer p head. And you're like, wait a second, you haven't made a node yet, right? So let's do that. So what is the difference between a struct and a node in C++? So I'm not going to use templates here. I might do a little bit of template demonstration later, but right now let's just stick with this because I want to actually finish this. And if we do templates and we do all the different types of things, then the problem is that it might take longer than like 20 minutes to code up. So let's do this in a way that it'll take a short amount of time. Yeah, so basically, at least in C++, yes. In a class, elements are private by default, and in a struct, they're public. That's why you don't have to write public here. You can, but you don't have to. You can, in C++, you can even create functions, like a constructor, for instance, for your new value, next. Cool. What'd I do? Oh, right. I'm using Python. Okay, there we go. My Python has totally broken my brain. I forget that you need types because it's not Python. Okay. All right, so let's do this, right? So you basically see that we have the creation operators, we have insertion, we have removal. We don't really have an update so much, but yeah. All right, cool. So this is what I usually do in order to code stuff. I will just copy paste right into the CPP file all of my functions like this. And then remember what you have to do. You have to go linky, and this is like the way to tell the compiler that it's a that it's coming from the linky class, right? So there we go. So exactly what I said, right? So if you remember what I did when I created a default linked list, all I did was I set phead to null pointer, right? So this will create an empty linked list, which is what we want. Okay? And so the creation operator, this is definitely not complex, right? You know, you don't have to integrate, you know, around the around some pole and, you know, 1/2 pi I. You don't have to do any of that. This is pretty simple. Okay, I'm gonna leave this for a second. You just sit here. What do you like? Uninitialized. I don't care. You just sit here. So, you know what? I'm going to add another method. One more method. We're going to get a getAtPosition method. Okay? And it's going to return an int. And it's going to take a position. Okay, cool. So now let's fix the .h file. So we wanted a get method. So it returns an integer. And then I messed this one up because I called it position. Okay. Cool. All right. And then maybe we'll make an output for it. So, like, this is just for debugging purposes. We'll make a print, right? You can also just do it as a cout thing. So let's just do a cout thing for it. So, yes, this is the copy constructor. Yes. This will take a linked list and it will make an identical linked list out of it. So, and then getAtPosition is just going to get the value at position, equaling. Why do you need a copy constructor? And the answer is basically this. Like in C++, if you have one linked list and you want to make a copy of it, and what I mean by that is you want to assign, or you want to say, this new linked list is equal to this old linked list, or this new linked list is some copy of the old one. We can't just assign the pointer to be we can't just take the other linked list's pointer and just assign it, because then that'll just be a shallow copy, and whatever you do to the first linked list will also happen to the second linked list, right? And so that's a huge problem. So that's why you make a copy, is because if you want to have another linked list that you can modify that won't affect the original one. Okay, so how do we getAtPosition? So I think one of the ways to do it is for int I equals 0, I is less than position, I plus plus. Okay, shocker, right? And so I'm going to create a node pointer called pCurrent. And you'll see that I do this kind of trick a lot. Well, I don't know if it's a trick. It's just a standard practice. I create a node pointer, and I just have it point at the head, right? So, okay, what is going to happen? So really what I want to do is I want P current to keep tracking ahead. So every time we go through a position, I want to assign P current equals P current to, dot P next, like that. But I can't quite do this, right? I can't just do this. And the reason why is, you know, maybe P current was null. So if it is, this is a seg fault, right? So how do I fix that? So what I do is I check to make sure that P current is not null. So if P current, and so there's a bunch of ways. You can always say if P current is not equal to null pointer, that's one way. The other way to do it is just to say if P current. Because if P current is null pointer, it will evaluate to false. So if P current is not null pointer, then you can do this. Okay. What if it's not? What if it is null pointer? What do you do? So if it is null pointer at any point here, so the idea here is that you have to advance to position P. Right, we have to basically return 0, or really actually what you probably want to do is throw some exception, like not found exception. Because returning 0 might mean that something was in there, right? I guess what we could do here is we could change it to return a node pointer, and we could literally just return null pointer like this, and so that way we could avoid having to do that. And then at the very end, what we're going to do is we need to return the P current's value, right? Oh, I'm sorry, we just returned P current now. So get at position is no longer going to return the value, it's going to return the whole node. And so technically this is a little bit unsafe because it gives access to the internal structure to the outside coder, right? They could start messing with the current pointers and all that stuff. They could start tracking their way through the linked list themselves. So that's a bit dangerous, but you know what? Cool, we're gonna do it anyway. All right, so this is kind of how you track through a linked list. You can do there's also a while loop version of this that you can do, and maybe I'll write the while loop version in the insertion. So let's talk about insertion now, okay? So is everyone more or less good with getting at position, right? So what you do to get something at the position is you will, basically to get, what do? Right? You will have a bunch of boxes, right? Here's a box, 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 and here's your next pointers, right? So if you want to get, so if this is at position 0, 1, 2, and 3, and you want to get something at position, say you want to get something at position 2, then P current starts here, and then you're like, nope, it's at 0, so I advance to 1. Nope, it's at 1, so I advance to 2, and then I return this node, right? So that's what you do, is you keep tracking through the next pointers until you get to the node that you want, and then you return that. So this is generally this is what you're doing when you get. So remember what we had to do when we inserted, right? So when we inserted things, there's kind of two ways that happen. So either, so when you're inserting, you have to remember that either you're inserting at the head or you're not. And that is, like, you know, shocking, right? You're either doing something or you're not doing that thing. But that, it changes what you're doing, right? It changes what's happening here. So what if you're inserting at the head? Actually, can I make, oh, I can. I should have done that from the start. I forgot about that. So what if we're inserting at the head? So that means if position is equal to 0, right? What do we do, right? And then I guess else. Well, really, I'm just going to return. Or maybe I'll just return here. So if position is equal to 0, then I need to create a new node. So I'm going to say node pointer, p new, equals new node value, right? Because we've made a constructor for our node class that takes a value. So I'll stick it in. So we need to make a new node pointer. And so the mistake would be to just say phead equals pnew, right? That would assign it to the thing, but then if you do it this way, then you might forget that phead had a next, or phead existed before, right? So instead of that, what you need to do is you need to say pnew arrow pnext equals the old head, right? You can do that first. So assign the old head to be the next node in the chain, right? And so now we have it. Okay. And so why do we return here? We're just going to return here instead of doing else. So now this means that position is bigger than 0, so we're not inserting at the head, right? So in this case, we have to be a little bit careful, right? So if we're not inserting at the head, let's say we're inserting at position, I don't know. Let me just do an example here. So if we're inserting here at, let's see. So let's say we're inserting here, and here is position, let's call it position x minus 1. This is position x, and this is position x plus 1, right? So if I want to insert a new node at position x, right, here's the new node. I'm not getting rid of this. This one is sticking around. So in order to deal with this, what I need to do is I need to keep track of the position x minus 1 node. And you might ask, why do I need to do that? Well, the answer is because I need to, so x is pointing to here. This one is pointing to here right now, but what I want to do is I want to get rid of this, and I want to reassign this one to point to here, and then I want to reassign this one to point to here. Right, so then this will be the new position x, and then this one gets plus 1, this one gets plus 1 plus 1, right? So now they don't know what position they're in. That's the whole point of a linked list, is that nodes don't really understand what position they're in, so we don't have to update all of the nodes to tell them, like, you've advanced one, right? We don't have to do that. But just mathematically, that's what this is. So when we're keeping track of position x minus 1, that means we need a previous pointer to keep track of where the previous node is, as well as the current one. So let me show you what that looks like. So, okay. So, I don't know, let's create node pointer p current is equal to p head. Well, okay, so dot p next, and this is actually a bug, but then node p current, p previous is equal to p head, right? So this is technically a bug because, oh wait, sorry, node pointer. So this is technically a bug because we don't necessarily know if p head has a p next. Like, just because I tell, like, the programmer tells you to insert at position p, does not necessarily mean that the coder is right? The programmer could be mistaken, and the length of the list could be actually a lot shorter than they think, And so they could be trying to insert a node way after the end, or even if the list is empty, right? They could be having problems. So how are we going to deal with this? So what we can do here is we can say if p head, or I guess actually we can say if not p head, right? We can return. Because what that's going to do, I mean, you might consider throwing an exception. In this case, it's just, since this is a void, it's not doing anything. Or you can return false for didn't insert, something like that. But here we're just going to fail, whoopsie. We're going to fail silently. So now we're guaranteed that p head isn't null. And so now what we're going to do is we're going to use the while loop business. So we're going to say while, so let's say int I equals 0, int I equals, int I equals 1, while I is less than position. And so what do we do while I is less than position, right? So, and for instance, we're going to probably want to check that p current is not null, right? Okay. So what are we going to do here? What we're going to do is we're going to I++ the thing, and we're going to say p current equals p current dot p next. But before we do that, we can assign p previous equals to p current. So remember what this is doing. What this is doing is it's saying the current thing we're pointing to goes into the previous thing, and then the current thing gets updated. So basically what this does is it advances the previous to the current, and then here it advances the current to the next, right? Okay. Cool. So, all right. So now, so basically here we're going to check to make sure that we reached the right position, right? Because if we didn't reach the right position, if I is still less than the position, then we're just going to return, right? So how do we insert? Well, we're going to create a new node. So we're going to say p previous, p next is equal to a new node with the new value. What's the new value? Probably called value. And then what we're going to do is remember p previous arrow p next used to be current. So now we have to relink by setting this new node here. So like there we go. So you see that there's a lot of edge cases here that can cause things to break, because either the position can be 0, so we have to insert the head, and then you have to check if the head is null, and if the head isn't null, then you have to go up to the position, but maybe you don't get to the position because maybe the linked list isn't long enough, right? But if it is long enough, then finally you get to do the thing that you wanted to do from the start, which is just create a new node and insert it. So you see that, like, basically this while loop and this stuff is what really is doing all the work. All the rest of this is really edge cases and safety checks, right? And that's unfortunately kind of what you have to do when you're writing linked lists, is that. Okay. Okay. So that takes care of the insertion. The only other thing we have to do, well, the major thing we have to do is removal. But it's actually very similar to insertion, right? So basically when you're doing removal, you still have to keep track of, remember what I said here, you still have to keep track of a previous, well, here's insertion. But when we do removal, it's still the same thing, right? When you remove, you still need to keep track of the previous node because the previous node is right here. And here's the next node. So you need to keep track of the previous node, the next node, and the delete node, right? So you don't really actually need to keep track of the next node. I'll show you why, but at least you need to keep track of the previous node and you need to keep track of the delete node. So it's basically the same as insertion. So, okay, let's work on it. So what do we do? So, okay, what happens if position is equal to, well, okay, so what happens even before position being equal to 0? What happens if not p head? Well, if not p head, you just return false, right? Element was not removed. Okay, cool. But what about if you do something else, right? So what about if you want to, say, remove something at the head? So now we know that, I mean, technically this is like else if, right? Else if position is equal to 0. So if the position is equal to 0 and, you know, and we haven't returned, so we know that the head has a node, then what do we do, right? What we have to do is we basically have to say p head equals p head dot p next. And then we're done, right? So this has two problems with it, right? So this does the right thing in the sense that it does actually advance to the right position and it forgets the thing, right? The problem is that it forgets the p head, and so it never deletes it. So that's a problem. And the other problem is that it, so okay, cool. Let's node pointer p old head equals p head. Now we remember it. Cool. And then what we can do is we advance this, and then no, we're not done. We still have to remember to delete the old head. So delete. Cool. So okay, so that's if the position is 0, right? What that's basically doing is that's crossing out the first node, right? So what that's doing is basically it's saying if this is the first node, if this is the head and this is the next, then basically what we're doing is remembering this is the old one. You set the head to be this node, and then you delete this node. So that's how that works. Okay, cool. But now what if it's not position 0, right? So what if it's not position 0? Then we have to do some kind of, then we have to scan through the list again. So we're going to create another current pointer. Well, actually we need two. We need p previous is equal to p head. And we know that node pointer p current is equal to p head arrow p next. And the only reason why this is safe is because if p head is null, then we've already booted out of this function. right? Otherwise, this line could cause a seg fault bogey. Okay. Okay, cool. So now we need to loop through we need to go through the thingy, go through the the linked list, and we need to, what do we need to do? I'm just gonna steal this code. Which code should I steal? I'm gonna steal this code. Code stolen. Cool. Because it's basically the same. Instead of, we'll return false if the position wasn't found. Instead of null pointer. And here, so this time we can just do this, but we also have to advance the previous pointer too. You know, don't forget the previous pointer. So p previous equals p current. And then p current is equal to p current.p next. And so that will do what we want it to do. That'll get us up to position p, or it will return false. So if it hasn't returned false by the end of this for loop, then what we know is that the position is now, or the position is now now correct. So what we have is we have the current node, we have the previous node. So how do we delete it? So first we have to check if p current, well, I guess if not p current, we can just return false. And else we can do the last thing. So what is the last thing we have to do? So, and why did I have to check it one more time? So I'll leave that to you to figure out. Why did I have to check this more time? And it has something to do with this for loop, right? Because every time, well, I won't say it, but I'm going to put this code up on the GitHub so you have access to it. And so basically, I want you to figure out, think about why I needed to do this, okay? Because if I don't do this, it's possible that it will actually be null pointer. Anyway, but why is that, right? Why? Think about why that happened. All right, and then okay, so finally, what we're going to do is remove the node. So remember how we have to remove the node. What we have to do is we have to set the previous node to the next, and then we have to delete this node. I'm just returning false because like I make it a Boolean here, and so if it removes correctly, it'll return true. And so I guess here we can return true, and if it does anything else, then it'll return false. Like that's the goal of this function, is basically if it works, it'll return true and says, I removed it for you. If it doesn't work, then it'll return false, and then the coder will know that nothing was removed out of the linked list for whatever reason. Okay? And then, all right, what else is there to say? Oh, right, we have to remove things. So p previous dot next is equal to p current dot p next. Now, we know two things. We know that p previous and p current are not null. We don't know p current dot p next isn't. But it's okay. And the reason why it's okay is that we set it to be the next pointer, but we never actually access it. We never go, after this, we never go like p current dot p next dot p next, right? We don't actually use the next pointer. So it's okay if this is null. And then what we do here is we still have the current. So p previous dot next is now equal to the next one. So now it skips over that one. And so now all we have to do is delete p current. And you might be thinking, well, doesn't p current still point to this as well? And the answer is technically yes, but we're deleting it, right? So now kill off the node. And then we return true. And this is not anything special. This is just because the function does that when it works. Okay. So that is insertion and removal in linked lists, right? And that's the code that you have to do, right? So the thing is that you see that, like, really in the end, this is exactly what our drawing was, right? The pprevious.pnext is equal to pcurrent.pnext, and delete the current node. But you have to think about all the stupid edge cases before you can get there. That's why this code is long. And so what I'm going to want you to do when you go home and, take this home to yourself and think about it is just think to yourself, like, is this, like, why is all this being done? And are there any bugs, right? Are there any bugs? Right? Because I could have left bugs in here because I haven't tested any of this. But, okay, so now let's get to the thing that you're all waiting for. You're like, I'm bored of this. I don't care about linked lists anymore. The implementation was dull. So here's a question. Was it helpful? Was this explanation helpful to understand how linked lists work? Before I get to the other stuff. Okay. So I will post this to GitHub. So if you don't understand the code, if you're thinking, man, I'm not 100% sure about exactly what he did, you know what you can do? You can download the code and write yourself some tests and see if you can break my code. And if you can, then we can work on debugging it. So, but anyway, now is the thing you've all been waiting for. This is all you ever cared about, right? Now we're ready. How do we make a copy of a linked list? So let me do a little bit of an explanation about how to do that. So here is a linked list, right? And that one's kind of a bullet shape, but it's the same as all the others. I don't know. And so now we want to make a copy. So the first thing we have to do is copy the head, right? Because this guy has a p head that points to this guy. And this one is going to need a p head. And you know the p head is always an edge case. So we'll create a new p head and we'll copy the value, right? So the value will get copied into here. All right, and so then this is generally how I do it. I have a read pointer and I have a write pointer. And so what I do is I say the read pointer is going to point one node ahead, and the write pointer is going to start at the new, this is the new one's p head, and this is the old one. And so what's going to end up happening is, what you do is you say, you create a new node if the read pointer isn't null, right? If the read pointer isn't null, if read is not null pointer, then you create a new node. You copy the value. I'll call this v2. Call this v1, I guess. v1, v2. You copy the value. And then you advance the read pointer to the next, right? So then step 3 is advance read and advance write. So then this becomes the write pointer, and this becomes the read pointer, right? Correct in the next step, right? So this becomes the read pointer, and this becomes the write pointer. And then you do it again. You make this node. You copy v3, I guess, and then you advance the and you make a pointer, and then you do it again, right? Then this becomes the read pointer, and this becomes the write pointer, and then you copy a node, and this is v4, etc., right? So that is generally how I do it. Can you come up with other ways to do it? Yeah, I mean, there's variations on the theme. Like, when I'm showing you this code, is this code the only way to do it? The answer is 100% no. There's a lot of different ways to code up a linked list. And I think they're mostly variations on a theme, but, cool, right? there's a whole bunch of different ways to do the same thing. So now let's look at, okay, so if other linky dot phead, so we don't have to use the arrow, right? Because other linky is not a pointer this time. So if other linky dot phead, then what we're going to do, else I guess phead equals null pointer. Wow. Okay, otherwise what we're going to do is we're going to create the first node. So we're going to say phead, this is the copy constructor. Right, in the default constructor, in the regular constructor, this thing is just going to set the phead to null, right? But in the copy constructor, it's actually going to make new nodes. And so we're going to say other linky, crappy, dot phead, dot arrow value. Cool. So then we have to do what I said. We have to make a node pointer pread equals or other linky. Remember what I did? I made it the other linky dot phead dot p next, and this is okay because we know that other linky dot phead exists. Right? If it didn't exist, then we'd have a problem. If it, blah blah blah, and then you assigned node pointer pwrite equals phead. And so remember that this is our new linked list, right? Okay, that's our new linked list's head. That's what it is. So, what else do we got to do? What do we have to try? What do we have to say? We just do exactly what I said, right? We say we say while pread, so while the read pointer is not null, we are going to create a new node, so pwrite.pnext equals new node, and we're going to take pread, values. I hate when it doesn't autocomplete, just enter sometimes, because I'm like, oh, I wanted it to autocomplete. And then remember, so then what we're going to do is we're going to advance, right? So this is make new node and copy. And this is advance. pread equals pread.pnext. pwrite equals pwrite.pnext. And so remember, pread is in the old linked list. And pread is the new linked list. The new linked list. Right? And at this point, we're done. That's it. Okay? That is it for a copy constructor, right? So I think this is actually kind of pretty unimpressive, right? So a copy constructor, let me show you what the difference is. So a copy constructor is where, so let's import linky.h. So linky L1, is some linked list. If you do linky L2, L1, this will invoke the copy constructor. But if you do linky L3 equal, and then you set it to L1, and then maybe some other stuff happens, but then later on you say L3 is equal to L2, then the equals operator will be executed. So that's when it is. And so yeah, that's the idea. Okay. So anyway, let's get back to I do want to finish this, so I know I'm going to take up some extra time, but I do want to actually finish this. And then next class we will test this out. We'll do testing on this code. So we'll see how much I've broken. And then what we're going to do is we will use this code to make stacks, queues, and decks. And we'll also talk about doubly linked lists and circularly linked lists. So we'll talk about basically all of the additional stuff you can do once you have this code done. And so let me just say that the equals operator insert temp data. Yes, but it's kind of inefficient because what you would be doing is you'll be inserting at the first one, then you insert and you trace through, then you insert and you trace through again, then you insert and you trace through again. When you're running this copy operation, you're only tracing through the linked list once. And that is better because otherwise you'll trace through the linked list n times when n is equal to the number of operations, or n is equal to the length of the linked list, and that's overall much less efficient. So what I'm going to do is I'm literally going to copy paste right into here. And then you say, wait a second, you can't do that. Yes, I can. I just did. So in order to return a linky reference, we're going to return a star this. Remember what star this does. So this is a pointer in C++ to the current class. So in order to return it, we have to dereference it. Yes, everything is going to be posted. Okay, so all of this is good. There's only one problem with this. There's only one problem. And the problem is that you can't forget what happens if the current linked list already exists. Okay? And so what do I mean by that? What I mean by that is maybe phead actually has something in it already, right? And if phead already has something in it, then we need to delete it. So if phead, right? So if it's not null, we need to go through this thing. Actually, we could even do it kind of trickily. We could say while phead, and then we could say p next, or let's say p current is equal to phead arrow p next. And of course, you're like, you haven't declared it. I know. I hear you. I hear you. I got you. I'm with you. All right. So p current is going to advance past the thing, and then we are going to, what are we going to do? I guess we should just do p current. Let's just do it. Let's not do it trickily because I think tricky is bad. So tricky is bad. This is non-tricky anymore. I was gonna try to do something tricky, but no. So while p current is gonna be equal to, and then we'll create a delete node. So we'll set this to be phead, and we'll set this to be phead.pnext. And so what we're going to do is we will advance it, and we will and then we will delete p del node. And I think this will, so currently it's the, I think at the very end we also have to delete phead. Because if you trace through this, what this is going to do is this is going to delete yeah, so what Liam was asking here was, can you simply, now that we've coded up this equivalence operator, this is the copy constructor, this is, he's already jumped to it, this is the destructor, right? This is the thing that if the linked list exists, will destroy the linked list. There we are. I think that works. I think that's all we need, right? I think we're done. This is p current because that's next, and so that will go until, yep, and then when this is false, then it won't delete it anymore, and that's good, and then the only one it misses, it just doesn't end up deleting the first one, it skips the first one. But the destructor is really just the same thing, right? Because the destructor says, if the linked list exists, then we, and I will say it's always safe to just set phead equals at the end, okay? You might be like, why are you doing this? Sometimes destructors are run on classes, and then those classes continue to exist. So it's possible, like, it's theoretically possible that if the class is, like, is destroyed, but not really, it can be used again. And so it's always good to reset this pointer to null pointer, just so that, like, the next time the class has an insertion operation, it'll say, I'm an empty linked list. Because if you don't reset the head to null pointer, you will delete the head, but the head pointer will still be pointing to that deleted node. Delete does not zero out the pointer. Delete simply deallocates the memory. Right, so delete will just deallocate the head. It doesn't zero the pointer. So, but anyway, right, and so basically what this is doing is it's just going through and it is doing this. It is saying, here is one node, here's two nodes, here's three nodes, here's four nodes. So what it's actually doing is it's saying, so here's current, and here's the delete node. So it's basically saying, like, advance current to the next one. So current gets advanced, and then delete gets advanced, and then we kill off this node. And then current gets advanced, and delete gets advanced, and then we delete this node. And then current gets advanced, and delete gets advanced, and we delete this node. You notice the one thing that doesn't happen is that the head doesn't get deleted, so at the very end, we come back in and we delete the head. Okay? So, I mean, there are multiple ways to do this. I don't think that you necessarily have to forget to delete the head. There are ways to do it better than what I did, probably. So, my code is not optimal. My code is simply literally what I typed in real time as you were watching. Okay, so that's it for linked lists for today. Let's reconvene on Thursday, and we'll talk more about linked lists, right? And we'll talk about stacks and queues and stuff. So, but I think that this gives you a huge idea about how to attack your project, right? Because, I mean, hint, hint, right? Let's see, what does this class have? Ah, yes. So you see here that this has one element in the class. Oh, I'm sorry. It has one element here. That element is, it's not p head, it's underscore head. Okay, right? But it's basically identical. So, and I think if you look at this stuff, if you look at enqueue, you'll basically see that this is sort of this is like an insertion operation. This is an insert at the end operation. It's always just inserting at the end. This is a delete from the head operation. So this is just the delete from the beginning operation that we talked about. And this is a Boolean function that determines if the thing is empty, which we could have added in one line. So, Okay, and this returns the head instead of our get function. So you see that a queue is actually a restricted version of a linked list. All right. Nice. All right, thanks everyone. Have a good rest of your day. Yeah. If you have any questions, any comments, any complaints, well, preferably don't complain, but otherwise, nice. All right. Yeah, I don't know. I'm gonna find out if you haven't gotten the Discord link, definitely send me an email. Because I will work on that probably tonight. I am sorry you don't have a Discord invite, but yeah. Okay. Yeah, I mean he's the one who manages the 341. So you can email Professor Johnson if you need to get into the Discord, and he should be able to get you in. Yeah, you should probably email him, but if you message him on Discord, he'll probably help you too. Yeah, once everyone's in, we can make ourselves a little class in there, just like Ben has, because we want to be special too, right? We don't want to let him upstage us, right? We have to outperform Ben's sections. Okay? Gotta beat him at his own game. Okay. I think that's all for today. I'll go and post this up on the GitHub, because that's what people like. All right, later.